We have a system of linear equations and we want to solve them, which means we want to find a value of x and a value of y such that these values of x and y satisfy this equation as well as this equation. Well, to do that mechanically, we're just going to do mechanical procedure here and say, okay, we multiply the first equation by 3 and the second by 5, and then we add the resulting equations. Now, I just gave that instruction, okay? So people do that. You multiply the first equation by 3, you get this. 3 times 3 is 9, 3 times negative 5 is negative 15, 3 times 2 is 6. So you get 9x minus 15y equals 6. 5 times 4x is 20x, 5 times 3y is 15y, 5 times 7 is 35. There are your two equations. Now we add the resulting equations. So 9x and 20x gives me 29x. Negative 15y and 15y gives me 0, which is why I chose those numbers incidentally. 6 and 35 is 41, so we get 29x plus 0 equals 41. Notice that y has disappeared, and now we have just one variable in a very simple equation, and we can solve that equation for x. We get x equals 41 over 29. Now, that's as far as we went on this problem because we got a fraction here. Now, what we would do with this number is we would then bring this number back into either this equation or this one, substitute it, and solve for y. Now, if this is correct, and if we correctly solve for y, the value that we get will work in the first equation along with this value of x and make that equation also equal. So that's where we're heading. So we do this set of equations. Now this time I just said, okay, there's a set of equations. Multiply both equations, or one equation, multiply something by something, and see if you can get one of the variables to go away. Well, there are two ways you can do this, okay? One way would be to multiply this equation by 2 and this one by 3, because then you'd have 2 times this equation would give you a 6x here, and 3 times this equation you'd have a negative 6x, and of course you'd have the values of the other parts of the equation that go along, but the x's would be equal and opposite, so when you add the equations they'd go away, and you'd have an equation you could solve for y. Okay? Now, about half the class did that. The other half of the class wanted to imitate what I did here and chose to eliminate y. Okay? And pretty much did that correctly, okay? And that's just as good. You get easier numbers. Numbers a little smaller if you eliminate x. And you've already got a negative and a positive if you want to eliminate x. So for those reasons, most people are going to choose to eliminate x. But there's nothing wrong with choosing to eliminate y. Okay, so you've got, here you got a 6y, here you got a 7y. Means if you multiply this equation by, let's say, 7, you're going to have 7 times 6y, which is 42y. And multiply this by 6, you're going to get 6 times 7y, which is going to be 42y. Well, if you did that, you'd have to subtract the equations to get rid of y, and that would work. But it's a little easier to add because you have a little less probability of screwing up the signs. It's a little easier to screw up the signs when you subtract. So we're going to choose to multiply, let's say this one by negative 7. Okay, well actually what we did, we multiplied this by 7 and this by negative 6. So 7 times the first equation, well you can see, I don't have to read it to you. You multiply 7 through here, you get this. You multiply negative 6 through the second equation and you get this. And you have a 42y and a negative 42y. So when you add the two equations, the y's are going to go away. You have a negative 14x and an 18x gives you negative 32x. 56 and negative 24 gives you 32. Negative 32x equals 32. Divide both sides by negative 32 and you get x equals negative 1. Okay? Then you take that value, and I'm using arrows. I like to do this. I'm not sure it's all that helpful for people, but you take the x equals negative 1 and you plug it in to one of these equations. Now I chose the first equation simply because it's easier to get the arrow to point to the x in the first equation. That one's, you know, a little harder to get to. So I just chose the first equation. I could have done it in the second equation just as well. Okay, so I replace that x with -1, and what equation do I get? Well, I get the same equation, but now x has been replaced by -1. I've still got my -2 in front of it. I've still got my 6y and my 8 and my equal sign, okay? And then I just simplify. You know, -2 times -1 is 2. 2 plus 6y is 8. We solve that for y. Well, that's easy to solve. I don't have to go through the steps of that. Y equals 1, okay? Then, gee, I don't know if I did this. And this is really kind of important, so I'm going to do it now. I'm so busy getting to the graph that I didn't bother checking the equation. We check using the second equation, which is 3x plus 7y equals 4. If I plug in x equals -1 and y equals 1, does this work out? Well, plug in -1 for x, I'll have my 3 times -1, and my 1 for y, I'll have my 7 times 1, and that should equal 4. Well, that comes out -3 plus 7 equals 4, and -3 plus 7 does equal 4, so I'm going to put a check mark there. So this verifies pretty well that x equals -1 and y equals 1 satisfy both of these equations. Now to completely verify, you could put -1 for x here, 1 for y here. You get 2 plus 6 equals 8, and that would check out. Okay? Now, next thing I say to do is, well, let's construct a graph of each of these equations. Okay? And to do that, okay, this time, there are two ways we could graph these two equations. We could find the x and y intercepts of each equation, draw a line through the x and y intercepts of one equation, a line through the x and y intercepts of the other equation. Or we could solve each equation for y and graph. I say solve both for y, actually, it would be more proper to say each for y. Okay? Well, the first equation, if you solve this for y, you get 4/3 plus 1/3 x. This is slope-intercept form. It's an mx plus b. Now I've got it in backward form of the way you usually remember it, but we know that the coefficient of x is a slope, and the other constant quantity on this side is your y-intercept. We do the same for the second equation, get the slope-intercept form. Then we graph, okay? Now, the intercept here, the y-intercept is 0 4/3. If x is 0, you get y equals 4/3. So you have the point 0 4/3, and that's on the y-axis. Right there it is. Here, if x is 0, y is 4/7. So you have the point 0 4/7 on the graph. Now, the slope of this graph is 1/3. So through the 0 4/3 point, we have a slope of 1/3. Okay, meaning from here, if we move in this direction, we're going to go down 1/3 here. So that if we start from this point and go up 1/3 and over 1, okay, and so forth. Anyhow, using the slope, we see that the line's going to look something like this. Okay? Now the slope over here is -3/7. That means if I was to move over 7 units, here I'd go down 3 units. Don't really want to move over 7 units, but we get that using the slope, we get a graph that looks something like this. Okay? And those two graphs cross at some point. Well, each graph consists of all the x, y points for which x and y satisfy the equation. Okay, you plug the x and y coordinates of any point in to the equation in this form, or the equivalent equation, the one we started with up here. And if the point really is on the actual line, you're going to get an identity. Okay? at this point, this one point, the x and y values that you get satisfy both equations. Okay, so what are the x and y values here? Well, just project down and project over from this point, and it looks like x is a little bit to the right of -1, say -0.9, so we'll estimate the point is has an x coordinate of -0.9. Over here, it's even closer to 1 than it was to -1 here, so I'm going to say that's maybe 0.95. It's really probably not that close to the way I drew it. So there's our estimate of the point of intersection. But we know the point of intersection has to be the point that we get from solving the equations, because these are points that satisfy both equations. Okay? So the point -1, 1 will be on the graph of both equations, and that's the unique point where the two lines, the two non-parallel lines, cross. Okay, well, that's kind of good. Okay, now, we move on to another system of equations. And we'll do that next. The thing I asked you to do was solve the system, okay? And I didn't write out the solution to the system, use the same method used over here. But you do get x equals 1, y equals 2. Now, the main task we did here was we graphed both of the equations to verify that that solution makes sense. So, we'll continue.